Okay, so I think in this video I'm going to go over a bunch of pericyclic and specifically the electrocyclic portion of the pericyclic category. And just throw a couple problems onto the board and work through them. I'm going to spend time talking about each problem, but I'll have timestamps down in the description so you guys can just jump to solutions and the next problem if you don't want to hear me ramble on about these problems. Um, anyway, let's get into the first one. Okay, so here I have just a cyclobutane ring, and it's got what looks like 4 substituents, and we need to add thermal conditions to this molecule to open the ring. So go ahead and give that a try real quick. Uh, so we can approach these electrocycle problems different ways. We can either use the acronyms, which I'll just mention, but I won't talk about much more. And they are DOT and they are COP. Standing for disrotatory, odd number of pairs of electrons thermal, and then you can probably figure out what COP means as well then. I like to solve these problems with my hands. I think it's a little bit easier that way to visualize what's going on. So I thought I'd do that. So for in this molecule, we have the 2 electrons or 2 pairs of electrons will be moving. The first one is from this end, and the second one is from that double bond that is already in place. So when electrons start to move, we can imagine the ring opening, and just regiochemistry-wise, we can just draw this down because we know at least these parts that I've drawn aren't going to change. So looking at the stereochemistry, we have our methyl groups, and our methyl groups I'm going to designate as my thumbs. And since we are an even number of pairs of electrons, our orbitals shouldn't be both up and down, since the ends are opposite. And so I'll draw what that means on the board in just a second, but instead, our orbitals should be opposites. Again, in this case, now I've changed from my thumb being the methyl group to the pinky because I want it to be on the outside. On this hand, it's still going to be the thumb. The reason I'm doing this is because I'm shown in the problem that this methyl group, this methyl group and this methyl group, they're doing the same thing. In other words, one is going out, and so the other one's also going out because they're both on wedges. So when you rotate them so that you get your orbitals to match up, so palm to palm, remember pinky is methyl group and thumb is the other methyl group. When you get them to come together, that's how they'll be. And then if I can kind of show my hands, now remember that pinky is one methyl group and this thumb is the other methyl group. So now they're on opposite sides. So we should see them doing different things when we open up the ring. And so we can depict that by drawing our methyl groups in right here. So if I drew that one cis, we know that the other one has to do the opposite thing. So I'm going to draw this one trans. Okay, so on this problem, we have something that's almost bicyclic, but we can make it actually bicyclic by doing just an electrocyclic reaction with it. So in that case, we're going to push around electrons by doing something like this. And that's just kind of inherent. That's the only thing really that we can even guess is going to happen. And so for the sake of regiochemistry, we can just draw exactly what we've just shown with our electron pushing. So we should have something just about like that. And this is supposed to be a straight bond. So that's that bicyclic part that we were talking about earlier. Again, with the hands, I guess actually first I should mention, the parts that we care about are the ends of our pi system. In this case, the ends of our pi system have some methyl groups that are connected in some way. And so that might be a little bit hard to depict with your hands. What'd be easier is just one substituent. And usually we don't really call it a substituent because truly it's not. But I'm going to call this H and this H the things of interest right here. So we have to figure out what are those H's going to look like over on our molecule. Because we have the regiochemistry, right? We just need to put down the stereochemistry. So again, we can do this with our hands. So we are in a thermal environment, so we're adding heat to it. Since we have an odd pair or odd number of pairs of electrons, our orbitals at the ends are both shaded the same phase. So I'm designating that by having my palms up. So under thermal conditions, and my H's, by the way, they're doing the same thing. So they're both going to be on the inside. So I'm going to let those be my pinkies. So pinkies right here. And it's thermal conditions. So just go ahead and rotate them into place. So you kind of see a little bit what my pinkies are doing. They're staying in the same place. So different from the other problem where we had something where they're on the other sides of the hand. So kind of one on one side, one on the other side. This is different. The pinkies are on the same side. And so that tells us they'll be on the same side when we close the ring. So over here, our product should have the H's on a wedge. Or you could put them on a dash. That doesn't matter. This is a mesomolecule. So dash or wedge doesn't matter. I'm just signifying that they're on the same side with these heavy dots. Okay, so now on this one starts out bicyclic. Recognize that we have thermal conditions, probably the easiest thing to recognize first. And then I would go ahead and try to figure out where our ends of the pi system are. So in this case, the only place that we can really see the beginning of a pi system are with these two double bonds. And I've told us that we're going to do something electrocyclic. So we can guess that opening this up to do this sort of an electron pushing is completely reasonable. And so if you're counting how many yellow arrows I've drawn, you'd say there's 3. And so 3 tells you that, if I turn on my camera real quick, 3 tells you that our orbitals are in the same phase. So again, odd number of pairs of electrons are going to be in the same phase. If I had an even number, it'd be like that. In this case, it's odd. I'm looking at the ends of my orbitals, so that's where, in this case, our H's are. And noticing the H's are doing the same thing. So I can either say, hey, they're both going to be on my pinkies, or they're both going to be on my thumbs. I just want to show that they're doing the same thing. So now with thermal conditions, I'm not going to change my orbitals at all. I'm just going to go ahead and match them up just like this. And notice our thumbs are on the same side. So when we open our ring, we should have our H's doing the same thing. So that means they're either both going to be cis or both going to be trans. Now I can look at this molecule and I know that I see a 6-member ring plus 2 carbons on the outside. It's not plus 4 carbons, it's plus 2 because 2 of the other 4 carbons and that cyclobutane are taken up in that 6-member ring. So that's really going to be an 8-member ring when we start drawing it out. So I'm going to skip drawing this messy and then recognizing it's an 8-member ring. I'm going to recognize before I start drawing it's an 8-member ring. It looks something like that, and I'm just going to put in my yellow arrow pushing. So my electrons that created double bonds, I'm going to put those in where they belong. And then the methyl groups at the ends that had stereochemistry, they're not going to change. We didn't do anything with them. Yeah, they're mostly there just to, I would say, just fool you, to get you to look in the wrong place. And then the H's, those are the parts that matter. We said they will do the same thing because we ended with our thumbs on the same side. So we should have an H coming out right here and an H coming right here, out right here. And you can convince yourself that is the regiochemistry of those H's. If you just go back to your original molecule and you count away from, well, really whatever you want. You could count from the double bonds or the methyl groups. It's your choice. But go ahead and convince yourself that is the correct spot for those H's. Okay, so this is the first problem with light that we are encountering. I think for the rest of the video, I will refer to this as just photochemical conditions. So this is H nu. And I guess we can go on to this problem. So go ahead and try to figure out what the product of this electrocyclic reaction is. So I'm going to go ahead and do what we've done with past problems. I'm just going to show my electron pushing. So electron pushing, I'm just going to show that pi bond going to attack the other side, and you'll get something like that going on. And so we start seeing kind of readily why we did this photochemically. If we looked with our hands, and I guess, again, I'm getting ahead of myself, I should designate where the H's are. So in blue, we care about this H and this H, because those are the ends of our pi systems. So those H's, they look to be both doing the same thing. So in this case, I'll call them, looks like they're doing, well, I guess you can't call it cis or trans here, but we know they're both going in the same direction. So I'm going to designate that with my thumbs. We should recognize that we have an even pair or even number of pairs of electrons. So instead of my hands being up like they are right now, I'm going to change one being down and one being up. And so that's just recognizing that there are an even number of pairs of electrons. So without going any further, you have to recognize, wait, we have photochemical conditions in play here. So that bumps an electron up from the previous lowest orbital that we were in. And so now if we were in an even number orbital, we'd now be in an odd. So that means we'd go back to our palms being both up. And so I said my thumbs, I'm going to stick to that. Those are my H's. And so when I rotate to get my orbitals together, so palm to palm, rotate them together, thumbs are on the same side. So in the final product, our H's should be on the same side. And so let's go ahead and draw what we think that would look like. That's not the best. Let's make it neater. There we go. And you could really clean this up and make it look a lot nicer. I think for the sake of the problem, this is probably easier to picture what's going on. And we said the H's, which same location, they're doing the same thing. Like in a previous problem, this molecule is meso, so in this particular problem, it doesn't really matter if we say that the heavy dots designate a wedge or if they designate a dash. It doesn't matter here. The big point is that they're doing the same thing. So let's go to the next problem. Okay, so I've gone ahead and drawn what really looks like actually 4 problems here. We can kind of see that, well, when we get to them, we'll see that really thermal conditions are just going to give you the opposite of the photochemical, and that works for most electrocyclic problems. So let's go into this one. We can notice that we have thermal conditions on the top going to the right. So top and to the right, thermal conditions. We have an odd number of electrons. So I can go ahead and show those arrows pushing electrons. Why not? And so let's go ahead and draw regiochemistry. And there's going to be our double bonds, and we have to figure out what our ethyl groups are going to do. So if I turn on my camera, the ethyl groups look like they're doing the same thing. What I mean by that is that they are both trans. So if one was trans and one was cis, I would say they're doing different things. But in this case, the ethyl groups are both trans. So I'm going to designate my thumbs as being ethyl groups. Now, my palms are facing up, and that's good because we have an odd number of pairs of electrons. So if you count those white arrows that I was using to push electrons, that's an odd number. And so we are in an orbital where the ends of our pi system are shaded the same way, or they are in the same phase, if you like that phrasing different, if you like that terminology. And so thermal conditions, you don't have to bump any electrons up. You just simply push your orbitals together, like I'm doing here. And I said my ethyl groups were my thumbs, and they are on the same side here. And so that tells you that in our final product, they should also be doing the same thing, being on the same side. So that was supposed to be a wedge. And I'm going to abbreviate this as ET. Now, I said that this was 4 problems in the beginning, but in truth, we can really boil it down to 2 problems if we really wanted to. And hopefully you can kind of see what I'm doing here. I'm just going to copy the regiochemistry that's going on in this problem. And then if we think for a bit, the thermal conditions give you the opposite of whatever the photochemical conditions are. And so if the thermal conditions gave you both on the same side, our photochemical conditions should give you opposites. So let's go ahead and draw what that would look like. And we should convince ourselves that this is true. So again, if we start with our palms up, I'm not going to designate what the ethyl groups are yet because I'm anticipating I'm going to change how my hands are oriented right now. But if we start with our palms up, because we know there are an odd number of pairs of electrons. But you also need to recognize that it is photochemical. And so although we started with our palms up, we have to bump an electron up one extra orbital. So if we start in an odd orbital, we are now in an even orbital. And we know that the phasing at the ends of our pi system are opposite in even molecular orbitals. So this is what we should have. Now our ethyl groups are doing the same thing. They're both trans. So my thumb is going to be one of the ethyl groups and my pinky is going to be the other ethyl group. So this is designating, like you can kind of think that, hey, they're doing the same thing. They're both on the outside. You know, this thumb's on the outside and that pinky's on the outside. So now when you try to match up palms, so when you match up palms, your thumb is right here and your pinky is right here. So they're on opposite sides. One is on would be my left side and the other one's on my right side. And so that's what we've drawn actually in our product, where they're doing opposite things, where one ethyl group is on a wedge and the other ethyl group is actually on a dash. So we could actually, I'm biting my tongue here, we can actually kind of go back and call this one problem, because we can kind of guess what the answer of the thermal conditions of this second part is going to be. So if you haven't tried it, go ahead and do that real quick. But I'm drawing regiochemistry, and I'll do that over here on the photochemical one as well, because none of that's going to change. And we can kind of go look and see that the ethyl groups on the previous problem were doing the same thing, and under thermal conditions, we got them on doing the same thing. And so over here, with our ethyl groups doing opposite things, we should expect them to give opposite results. So we can guess this is going to be our product for that. And then over on the photochemical, just do the opposite of the thermal in this case. And that would be with your two ethyls doing the same thing. So either both on a wedge or both on a dash. Again, this is meso, so it doesn't matter if you said dash or wedge. Let's convince ourselves real quick, convince ourselves that we can get to these products. So starting right here where the smaller yellow star is, I'm going to go to the right. So I'm going to be doing the thermal part of the problem. So we have an odd number of pairs of electrons. Our ethyl groups, one is trans, one is cis. So I'm showing them like this is my pinky for one ethyl group and this is my thumb. So they're doing opposite things. So when you put them together, so palm to palm, under thermal conditions, pinky, thumb. So they're opposite. And that's what we said would happen. So if we went over to the photochemical, we're starting with an odd number of pairs of electrons. We have a photochemical condition. So that means that we are changing our molecular orbital, our lowest unoccupied molecular orbital, or sorry, highest occupied molecular orbital. So the HOMO. And the ethyl groups are still doing opposite things. So pinky out in this case. And so when you put them together, the pinkies match up on the same side. And that's what we've indicated in our result. Okay, let's talk about this problem. It's in truth not a very difficult problem, but go ahead and give it a try and I'll talk about the small caveats to it. So I said a small caveat, there's not really a lot to it. It's just this is a problem that if you weren't told it was an electrocyclic reaction, like I've told us up at the top, you might suggest other things are going to happen. And I can talk about those other things in a separate video. I'm going to try to stick specifically to the electrocyclic part of, or electrocyclic chemistry, and I won't go into sigmatropic rearrangements right now. But that's a hint to what could happen, or what you could think would happen. In this case, actually, we're just going to push electrons like we would usually. So doing something just like that, we can draw the regiochemistry. It's always a good thing to do, just to organize our thoughts. And I've made a mistake with one too many bonds. So we'd have this thing going on. And then recognize, oh wait, there is no stereochemistry. So there's actually nothing you have to take in consideration here. You don't have to worry about which way your hands are rotating. You just have to recognize, okay, I'm going to open this ring. And when I open it, all of my substituents are going to, they're going to be on a double bond. So there's going to be no stereocenters here that we have to worry about. So let's do another one. Okay, so this is an interesting problem. Just because it, in truth, gets kind of messy, but that's okay. Recognize it's thermal and go ahead and try to figure out how many pairs of electrons we're going to do and try to determine what the product will be. So for this problem, again, it's thermal conditions. I'm going to go ahead and push electrons, just like this. And that helps me determine how many pairs of electrons I have moving around. So it looks like there are 3 different pairs. So that means I'm an odd number up in my HOMO for my pi system. Now I need to determine what is the end of that pi system. And in this case, that is this H and this H. And that is simply because that is the end of where the pi bond comes from. So those 2 H's are going to be our ends. So when we use our hands to try to figure out what's going on, so those H's, they're doing, right now, they're going to be doing the same thing. So as we open the ring, and actually let's go ahead and draw our regiochemistry. It's a good trend to do just to stay consistent. Recognizing it's a 6-member ring plus 1 when it opens. So I'm dealing with a 7-member ring. I'm going to do my best to draw that. It does get messy when you go past 6. And then I'm going to fill in my, my double bonds. So it looks like we should have something like that. Now, again, where are the H's and what are they doing? You can kind of look at this and determine that this is the most stable conformation, so we don't really have any way that we're going to twist this that will reasonably work. You can probably try with a model kit and you might break your model kit. And what I'm getting at is that the H's right here, as we depict them right now, it looks like they're doing the same thing. So they're both on the outside of our ring. Trying to put them on the inside of the ring would be actually quite difficult. And again, you might break a model kit trying to get that to happen because you'd have to twist your kit in awkward ways. But you actually don't actually need your hands for this problem. If you just recognize that sort of stereochem or steric effect in this problem, we can go ahead and use our hands if we wanted to. So if the H's are both on the outside or they're both doing the same thing, because they're going to be doing whatever the cyclopropane is not doing. So I'm going to just say they're on the outside. You could say they're also on the thumbs. It doesn't matter for this problem. And then it is thermal with an odd number of pairs of electrons. So I'm just going to say thumbs are my H's. And when I put them together, they're doing the same thing. So the thumbs are still on the ends. So hopefully in our product, and it looks like we did it, the H's are on the same side, doing the same thing. And again, it'd be kind of awkward if one H was going in like that and the other one was going out. That'd just be weird and it'd probably break your model kit. So. Okay, so it's a little bit different problem. If the problem asked to take the cyclobutane and heat it up, would you get more of this isomer or would you get more of this isomer? So go ahead and try to figure that out. So I'm going to approach this problem the same we did for all the other electrocycle problems that we've done. I'm looking at the ends of my system, and if you don't recognize that right away, that's okay. Go ahead and push some electrons around until you see it. And then I can recognize, okay, well, these methyl groups are at my ends. I'm also recognizing that I have an even number of pairs of electrons. So instead of my hands being both up, one's going to be up and one's going to be down. And I can go ahead and keep my hands in this configuration because I'm under thermal conditions. I'm not going to be bumping any electrons up, and so this is a pretty safe spot to be in right now. Now, the methyl groups are both doing the same thing. So they're both on a dash in this case. So I'm going to just go ahead and say that my thumb on what's my left hand and my pinky on my right hand are going to be like dashes. So in other words, they're doing the same thing. So when I bring my palms together, like this, my pinky and my thumb look to be on opposite sides. And so I have to find something. Well, actually, I guess we should translate that. So what does it mean when my thumb and my pinky are on opposite sides in this case? Well, that should mean that I have one double bond that is going to give me, or is going to be cis, and another double bond that is going to be trans. Okay, if they're both on the same side, then you wouldn't really be able to make a distinction, because you could say they're both cis or they're both trans, and we wouldn't have a distinction right there, unless there's something like sterics that gave that away. So in this problem, we have to look for which one gives you a cis and which one gives you a trans double bond. And so we look at this one and we say, okay, this one gives you both trans, and so that's a not good answer. And this one, well, that's your trans part, and this is your cis part. And so that's a good answer. So the second circled problem, or the one on the left, is our answer to this problem. It is good to note that if you ever saw this on like a multiple choice test, and they said, what are the possible products? This would be something like 99%, and you might see this 1%. So this might show up, but in very, very, very small quantities. So it'd also be kind of a main question if you saw something like this, where this was an option and this was an option. So let's go on to the next problem. Okay, so this problem is kind of interesting because it teaches you some useful techniques for changing stereochemistry. If, say, you made some molecule that had the opposite stereochemistry that you wanted. So in this case, we have to somehow make both of these H's do the same thing. So they're taking this H, looks like they're leaving it the same, and they're taking this bottom H that's on a wedge and turning it, or it's on a dash and turning it into a wedge. So we have to figure out a way to do this. And I should note that you can only use light or heat.